Okay, so in section 4.10, we will work with antiderivatives. So the purpose of this section is the following. So first of all, we will define the most general antiderivative of a function. Then we will define and understand the notation of a definite integral. Later on, we will learn a rule about a power rule for integrals. Let me first erase this. And then finally, we will do some examples and applications. All right, so let's start with first defining the antiderivative of a function. So definition. So the antiderivative of a function is the following. All right, so let f, capital F and lowercase f be functions. Then capital F is an antiderivative of little f if the following happens. The derivative of capital F is equal to lowercase f. And this is very important. So and what we'll do is, now notice here that there is this an antiderivative phrase, and this basically means that this is not unique. Okay, so let me give you an example. Okay, so let, for example, little f be 2x. Then we can have various options for capital F. So then let me just say an antiderivative of the function little f is a function whose derivative is little f. So an antiderivative of f is, for example, you can take the function x squared, or you can take the function x squared minus 5, because you know that if you add a constant or subtract a constant to a function, it doesn't really change the derivative. So you can have many options here. So for example, you can have x squared plus 100, or x squared I don't know, plus pi, etc. Okay, so you have many options. All right, so if you draw all of these antiderivatives on a graph, you have the following. So let me do, all right, so here is the function y is equal to x squared, right? Or the first antiderivative, this one right here. All right, what about the other one? So if you add a constant to a function, then you shift the graph of the function up or down depending on whether the constant is positive or negative. So for example, if you add 100 to the function, so if you add this 100 here, then you shift it up by 100. So let me just use a different color here. So for example, this purple. So this would be, for example, x squared plus 100. Or if you subtract 5, then you have a different one. So you shift it down by 5. So for example, this could be the graph. And so on. So basically these never touch each other. So this is a actually well-known fact, but we won't go over this in this class. So these are all antiderivatives, and these don't touch each other. Oops. Sorry about that. All right. So let me move on then to define the most general antiderivative of a function f. So note here that we have various choices. So we have this choice here, this choice. So you have various choices for an antiderivative, and the only difference between them is the constant at the very end here. So basically, if you take this x squared and add a general constant c, and depending on the value of c, you'll get a different antiderivative, which means that the most general antiderivative of a function is the function x squared plus c. So let me make that definition. So the most general antiderivative of little f, so let's suppose that capital F is an antiderivative, is the function f of x, capital F of x, plus c, where c is a constant. Okay, and this is called the most general antiderivative of the function. All right, so for example, the most general antiderivative of the function 2x is the function x squared plus an arbitrary constant c, so c is a constant, and so on. So another example would be the following. So let's say we do cosine. So the most general antiderivative of the function cosine x is, so now you have to think of a function whose derivative is cosine, and I think we all know that that function is sine, so sine x. And now you can add any constant to sine, and then you get the same derivative cosine, so you add the general constant c. And so on. Let me do one more. So let me do two actually very important antiderivatives. So again, the most general antiderivative of f of x equals e to the x is, as we all know, a function whose derivative is e to the x is e to the x plus the constant c. And then the next example is something which is, I think, different from the other ones. So the most general antiderivative of 1 over x is ln of absolute value of x. This absolute value here, this absolute value is very important, okay? Because if you don't put the absolute value around x, then you're assuming that x is positive, but in the function f of x is equal to 1 over x is not necessarily positive. All right. So now this most general antiderivative has a different name. So this is called also the definite integral of the function little f. So let me write down a definition. Okay, so definition. So let me make this actually red because this is important. Okay, so the indefinite integral of the function f is the most general. Well, let me write it this way. So first let me write the notation denoted by this. So read this as the integral of f with respect to x. So this is the notation for the indefinite integral of f. So this is the most general antiderivative of f. Okay, so let me highlight the important things here. This is important, and this here is also important. This is new notation now. Okay, so let me give you one example. All right, so the integral of 2x dx should be the most general antiderivative of 2x. And according to the example we did before, this should be the same as, so let me show you the example. So here we did the example of 2x. So we said that x squared minus 5, all of these are antiderivatives. So the most general antiderivative is x squared plus c. Okay, so let's go back and write this down as an integral. So now the integral of 2x dx is equal to x squared plus c. Now, of course, later on, we will define the definite integral in chapter 5, and then also define the indefinite integral in this way using the same notation. And then we will relate the derivative and integral using the fundamental theorem of calculus. So this is basically preparation for chapter 5. All right, so let's do some more examples of the indefinite integral. All right, so let's do the integral of, let's say, sine x dx. Now cosine x has derivative sine x, so negative cosine x has derivative sine x, which means the integral of sine is negative cosine. So another example, for example, the integral of e to the x dx is again e to the x plus c. And let's say the integral of 1 over x dx is ln of absolute value of x plus c, as we said in the previous examples. All right, now what about a question like this? What about the integral of, let's say, x cubed dx? Now we know that whenever you have a polynomial, then the derivative of a polynomial decreases the degree by 1. So now if you integrate, you have to do the opposite because you're finding the antiderivative. So you have to increase the exponent by 1, but you also have to divide by that number, because when you find the derivative, this exponent will come in front here, so it has to divide, it has to simplify with this denominator here, plus c, since x to the power of 3 plus 1 over 3 plus 1 prime is equal to 3 plus 1, which is actually 4, times x cubed over 3 plus 1. So this cancels that, so this is x cubed. All right, so I hope everything is going fine so far. So now we can introduce you this general rule for integrals, and it's called the power rule for integrals. So again, this is important, so let me highlight this. Okay, so it goes like this. The integral, the integral of x to the power of n dx is equal to x to the power of n plus 1 over n plus 1 plus the constant c, as long as n is not negative 1. Maybe I should do this. Let me just take this and move this here. Okay, this is better now. Okay, and I'll take this and move this here as well. All right. So you can take any power of x and integrate it as long as the exponent is not negative 1. So for example, the integral of x to the power of negative 73 should be the same as, should be equal to x to the power of negative 73 plus 1 over negative 73 plus 1 plus c. So this is x to the power of negative 72 over negative 72 plus c. Okay. Now there are other rules for integrals, which you'll learn later, but for now let me give you two more properties for indefinite integrals. So let's say properties for indefinite integrals. And we do have similar rules for derivatives as well. So the first one is, so the integral of f plus g is equal to, sorry, I should also write dx here, so let me do that, is equal to the integral of f plus the integral of g. And if you want, you can also put a minus here, and then it's the same rule. So the integral of a sum or a difference is the sum or the difference of the integrals. Okay, and the second one is, if you have the integral of a constant times the function, then this is the same as c times the integral of the function. So basically we can move constant coefficients outside of the integral. So let me make this red. Okay. Alright, so for example, now we can do more general examples than what we did before. So for example, if you have the integral of e to the power of x plus x squared, then this is the same as the integral of e to the power of x plus the integral of x squared. So this is equal to e to the x plus c1 plus x cubed over 3 plus c2. Now c1 and c2 are arbitrary constants, so you can combine them to a single constant. So e to the x plus x cubed over 3 plus the constant c. Alright, so let's do one more. So for example, the integral of the function, let's say 5 over x minus 3 times cosine x dx is equal to the integral of 5 over x dx minus the integral of 3 cosine x dx. So now you can pull the constant coefficients out. So in the first one you can pull 5 out, so this is equal to 5 times the integral of 1 over x dx, plus in the second one you can pull 3 out, sorry, this is minus, not plus. So the integral of cosine x dx according to the second rule, right? So this is equal to 5 times ln of absolute value of x minus 3 times sine x plus the general constant c. And so on. So you can do your favorite example this way. Alright, so let's do an application now. Now remember, last semester we worked a lot with velocity and acceleration if you're given the position function. Now in this section we're going in the opposite direction. So if I give you the acceleration function, I can say something about velocity and position function. So let me remind you. So suppose an object is moving in a straight path. Then we have the following. So if you say that st is a position function, then the velocity function vt is the derivative of the position function. And the acceleration function aft is the second derivative of position, which is the first derivative of velocity. So this is acceleration. So basically this means the following. If you go from position to velocity, you take the derivative. And if you go from velocity to acceleration, you take the derivative. So if you want to go backwards, you take the antiderivative. So let me write this down. So let's say S of t is here, and you have Vt and then At. So if you want to go in this direction, take the derivative. If you want to go in the opposite direction, then you take the antiderivative. So this means that if At is given, then Vt is an antiderivative of At, and St is an antiderivative of Vt. So let's do one example in this setting. All right. So we have a car is traveling at a rate of 88 feet per second when the brakes are applied. And at this moment, the car starts decelerating at a constant rate of 15 feet per second squared. Now the first question is, how many seconds elapse before the car stops? So to know that, to find that, we need to know the velocity function, and then set the velocity function equal to 0, which means the car has stopped. So we need to find v of t. Now v of t is an antiderivative of at, which means it's the integral of at dt. So this is equal to the integral of, now at is constant, so this is 15. So the integral of a constant is just 15 times t plus c. We're also given that the initial position, which is v0, is equal to, so it's right here, 88 feet per second. So this is 88, and this is also 15 times 0 plus c. So c is 88. So finally, we can say that the velocity function is 15t plus 88. All right, so now we set the velocity equal to 0 because that's when the car stops. So this means that 15t plus 88 is equal to 0. So this is equal to... Okay, so I think I did the same mistake again here. All right, since... Let me go back here a little bit. Since the car is decelerating, then this should be negative 15. So maybe I should make that red. 1 second. So this is negative. This is also negative. This is negative. So all the 15s become negative. Alright, sorry about that. So this is also negative. So this is equal to 0. And now this implies that t is equal to 88 over 15. And this is about 5, let's say, or a little more than 5. So that's the time when... actually closer to 6. Right, so this is the time it takes for the car to stop. And the next question is, how far does the car travel during that time? Well, to find how far the car travels, we need to know the position function. And the position function is the integral of, or the antiderivative of, the velocity function. So we have to integrate 15t plus 88. And we're assuming that s, the initial position, s0 is 0. Because we're counting how far the car travels when the time it stops, from the time it starts decelerating to the time it stops. Okay, so let's first find the integral. So this should be 15t squared over 2 plus 88t plus c. And we also know that s0, which is the initial position, is 0. So 0 is equal to 15 times 0 squared over 2 plus 88 times 0 plus c. So this means that c is 0, right? Because this is 0, this is 0, so c is 0. All right, so now we have our position function. So our position function is equal to 15t squared over 2 plus 88t. And now to find how far the car travels, then we just have to plug in 88 over 15, this quantity here, into the position function. So let's do that. So s of 88 over 15 is equal to 15 times 88 over 15 squared times 1 over 2 plus 88 times 88 over 15. Alright, so if you do that calculation, this is approximately equal to, let me just double check, this is approximately 258 feet. Oh, again. Alright, so again I need the negative sign here. Okay, sorry about that. I keep doing the same thing again. This is negative, this is negative, and then negative, negative, and then negative. So this is equal to approximately 258 feet. Alright, so as you can see, you can do many applications with antiderivatives, which we now call also indefinite integrals. And in chapter 5, we will drop using the name antiderivative and only use integrals. But we'll first have to establish that. Alright, so that's it. See